बैक करके वो कुछ भी कोई बग था, we are live now. क्या हो गया था? कोई glitch होगा. Now it's working fine. ठीक है? We are live now.
Start.
It is live now.
Okay, so let me start. What I'm going to talk about is much more simpler than the talk that you have heard. And I see a few of the stat students, so mostly it would be accessible. So, talking on condition time of 3, I should say independent random walks. Okay, so let me just do it by graphically. So 3 random walks are starting. So this is the space. So 1 is at 0 and 1 is at say 2i, and the other random walk is something or minus plus 2i and minus 2j. Okay, and 3 random walks are starting from this, and the time is on this direction. So let's say this one goes here, this goes here, here, and this. Something like this. This is the hit first time. So we are looking at the first time when one of these 3 or 2 of these 3 random walks hit. So let us now introduce some notations. So Sn, let's say k is starting point is 0 of k, and sum j equal to 1 to n I j k. K is either 0 plus 2i or minus 2j. So 3 random walks. So since this is the first random walk, the increments of this are, I am saying ij of 2i, and this random walk I am saying the increments of this ij of 0, and this is ij of minus 2j. Okay, and these are independent families. So ij k equal to 0 to I minus 2j, and j bigger than equal to 1, IID plus minus 1 equal to half. Right? And so I
There are 2 J's. There's 1 J signifying 2 things.
Okay.
2L,
Sorry,
start from 2L. Start from 2L.
So instead of j, I should do something like L or time t. Time is better. T is t. And this is probably I should do.
And that's okay.
Okay. And what we are interested in is the first time one of these 3 pair collide. So tau collision is, so either Sn 0 2i equal to 0 or
That's not possible.
just so one of these 3 pair are meet for the first time. Okay. Now here, as already pointed out by both Antar and Rahul, is that this part is not possible in this case. Okay. So in this part, so I'm defining it like this because of other reasons, so which will probably come to the end of this talk. So this will happen before this happens. So now one thing that we first note is that this tau collision, of course, is finite with probability 1. Okay? Because we know that any two pair of random walks will meet for sure with probability 1, as I have been told by Kumarji in the previous. So any two IID random walks starting from two different positions will meet for sure. So for example, these two will meet, and that probability is 1. So this is obviously smaller than these probabilities. So this is finite ownership. Now, one thing that Kumarji did not say, we'll come to that, is what is the expected time? So what is the expected time of, so let's have this tau 0 and 2i, which is, let's say, infimum of n bigger than equal to 1. Sn0 is same as Sn. By the way, I started with all 0, 2i, 2j, 2i minus 2j, because they have to be of same parity. If they are different parity, they will not meet. They will cross over each other, and they that they are equal. That will not happen. Okay, they will cross each other. Okay, so this we know is finite probability 1, but the expectation of tau is plus 2. Okay. So now but a strange thing happens for this tau collision. What we already know is that actually this expected of tau collision is actually not the expectation not only is finite, we know the value of this, and which is 2i times 2j. This is already known with Kumarji and two other authors from Lille. We wrote a paper of this. Okay. In this lecture, what we are going to say about the moments of this, higher moments of this. So theorem. Let me write. So expectation of tau collision is less than equal to, okay, there is some constant depending, okay, sorry, I will, for 0 alpha less than 1, there is some constant which depends only on alpha, and 2i 2j and 2i plus 2j to the power. Let me check the exact expression. Alpha times a constant. So this is that. Okay. So the moment is finite for up to 1 plus. So I mean up to 3/2. Less any power less than 3/2, and it is believed that expected tau. So this is I have not seen a proof of this. So this is infinity. So this is what it is believed. So that this is finite. This was there in various papers, but that there is a bound like this that was not known. Okay. That, and this is believed that this expectation is infinite. Okay. And but there is no proof of this at least that I know of any proof. Okay. So this is the part of this is a theorem for joint work with Maruf, who is here. I've been doing all the dirty work. So I'll give a sketch of this proof, and this requires two things.
question. How tight is the bound that asymptotically this is the best? That
Which
as
term?
I and j becomes large, your C alpha is the constant which you get at the limit.
What do you mean by
Your upper bound
Yeah.
is it tight?
sorry. I mean, the constant does not depend on ij.
No, right. But what I'm saying that
And as alpha goes to
not alpha, I and j becomes large. Whether you reach C alpha.
we have not studied that. Okay, so for that we require two lemma. Lemma 1. So let's say, okay, let's say I have xn a some non-negative random variables sequence measurable with respect to some sigma algebra fn. So this is filtration. So in general, essentially fn can be taken to be the sigma algebra generated by x1 up to xn, and in this case sigma algebra generated by I1, I2, In for all the three random blocks. Okay. And we need suppose for gamma less than beta. For gamma less than beta, xn plus 1 to the power beta given fn is less than equal to xn to the power beta minus some constant, okay, c times xn to the power gamma. On the set, oh, okay. I have to define one more quantity for the okay. So for we have xn non-negative, so we define something called tau b is the heating time of this. So xn is remember a non-negative field. So is the infimum of n such that infimum of n greater than equal to 0 such that xn is less than equal to on the set suppose such a there is some a which is for 0. A can be 0 also, a can be positive also. Okay. Then for any b which is bigger than maximum of bigger than or equal to maximum of a, and the strange constant is c divided by c into beta minus gamma by beta, whole thing to the power 1 by beta minus gamma. Expectation of tau d.
You are assuming beta is bigger than gamma.
Sorry. For any b naught. So this is the starting point of the chain where we want to start, and tau b to the power beta by beta minus gamma, given x naught equal to b naught. This is less than equal to some constant c1 which you can write down times b naught to the power. So what? So this is a if we have some kind of decay like this on xn whenever xn is large enough, okay, so this beta and gamma there are arbitrary numbers, except that these are gamma should be smaller than beta. Okay, and then if we start sufficiently high, so this is whenever we are above that a and some constant which comes from this beta and gamma. This c also we can write down this expression. There is an expression for this. Then we have a bound for the stopping expectation of the stopping time or the hitting time of the set b for any b. We have to start from any b naught, which is bigger than these two parameters.
You just want xn on the set xn bigger than or tau a bigger than n.
No, so
Yeah, the condition. I mean, it could be like that. You just want on the set xn bigger than
or xn bigger than a. Okay, whenever xn is bigger than a, we have this kind of form. So suppose that such a bound exists. Okay.
the process already come below b in some previous.
So A may be in fact 0. So that's we will have such a case. Okay, so this is lemma 1, and I will come to lemma 2. So lemma 2 will require one definition. So this xn process that we have to take is now define a xn process, which is, so remember, come back to this. So this gap that we see, so we'll call this gap, let's say d1n, and we'll call this gap as d2n. Okay, d1 is a gap at time n. What is the gap between the first the top process on the top and process on the middle, and d2 is the process on the middle versus the top process in the bottom. Okay, so what is the gap in? Okay, so this is what we are going to define. Oops. So so this is what the definition of dn, and we take xn minimum tau con. This is the process on which actually will show that such inequality is there. Okay, so let's take yn to be xn n minimum tau, and then what we will have that. So this is lemma 2. Tau plus 1 is less than equal and given then is less than equal to n times c1 alpha one into the power alpha. Okay, so in this case, our beta is equal to 1 and gamma is equal to alpha by alpha. Look at this, and this is true for all, actually then an a equal to 0. Okay. This is what we will get. Okay. Once we have both of this, the result will follow. Now let's sort of assume both of this, and we will see that. So proof of theorem. Let's we want to give it sort of proof of theorem. Okay. So what is that we require? So remember, we get here tau b, right? So tau b is remember this is bigger than equal to this b. I mean for any b which is bigger than this, and for b like this. So let's define. So take b naught to be equal to this constant, and this constant what we can calculate. So let's b naught is a constant which is a maximum of 0. Maximum of 0, in this case a is 0, and this constant is c times beta minus gamma by beta to the power 1 by beta minus gamma. This part is always less than equal to 1. Okay, this part is always less than equal to 1. So this is the whole thing to the power. So essentially the whole thing, this becomes c to the power 1 by beta minus gamma. And the constant that we get from here, using that, what we will get, this is less than equal to 4 by alpha 2 whole thing to the power alpha, alpha, and that is so. Sorry, so this is 4 by alpha. That is the estimate that we will get. Okay. So this constant, I am not writing down the expression. The expression is exactly will involve 4 times this and a constant which is less than 1. So that part will be less than 1, and only we will get this 4 to the power alpha by alpha, and therefore we get 4 to the power alpha over 2. But as we are looking at when this has to be for whenever yn is bigger than 0, right? Because on the set, this inequality is xn bigger than a, so that is yn is bigger than 0. So yn bigger than 0 means that this is bigger than 0. So that is that there is no collision. Note that when at time of collision, what happens is that so we have time of collision, one of these two, but must become 0. So this will have become 0 by that time. Okay. So xn becomes 0 at that time and will remain at 0. So it means that at time of collision, this yn has become 0 and will remain at 0. But when we say that this is positive, that means n is strictly bigger than tau of collision. So if not xn, yn is bigger than 0, this implies n is bigger than tau of Paul, and that will
is less than.
n is less than tau of Paul. Okay. And then that would imply that dn 1 is at least 2, dn2 is at least 2, right? So then yn will be bigger than equal to 2 times 2 times 2 plus 2 to the power alpha, which is 4 to the power 1 plus alpha. So this value is always bigger than 4 to the power 1 plus alpha. So if we set our b to be exactly equal to, so if we set, so if you look at now, note this tau of collision is obviously bigger than equal to tau of b naught, because this is hitting 0 and this is hitting less than equal to b naught. But note, if it is strictly bigger, then what would have happened? If it is strictly bigger at time point tau b naught, it would have been less than b naught. But any positive value of b naught, there the maximum value is 4 to the power 1 plus alpha, which is smaller than b naught. Okay, so that would mean that if it cannot be less than b naught, it has to be bigger than. The b naught value is this, right? So that in, but this implies, this fact implies that tau collision actually is equal to tau of the. And now therefore we just plug these values in this inequality, and tau b is now exactly tau b naught is exactly our values. Yeah. So this is because tau. So plug this in this inequality. I have messed up in this. B naught will be like this. The result statement I have mixed up. The result statement just for b bigger than b bigger than this, and y naught. Sorry, so this is x naught for any x naught. This should have been listed. So, and once we have this, we just have to plug in back this result, and that gives you the result theorem, proof of the theorem that we find. Okay, so then I'm not going to the details. Now we just I just show you how to sort of sketch this lemma 2, which is essentially a martingale calculation. Okay. So essentially we want to write down this expectation of dn1, dn plus 1, dn plus 1, 2, and dn plus 1, 1 plus d plus 2 to the power of dn. So this calculation that we need to do. Okay. And you see dn plus 1 is nothing but dn plus increment of in plus 1. So I have the first one is 2i minus in plus 1, 0. And similarly dn plus 1, 2 is dn plus. So you write down these expressions, the product of this, cross product of this, cross product of this, and use this fact that so alpha, remember, is between 0 and 1. So f of x plus h. So if I sort of expand this, is f of x plus h, f prime x plus h squared by 2f double prime of x, double prime of c, where c is between x and x plus h. Just see the derivative, second derivative is negative, so therefore, or it would be less than equal to fx plus h f prime x, and you just put it back. So this dn plus d2 is going to be less than this is the h part. This sum would be the h part, and h times the derivative. So essentially, just write down these expressions, and what you will end up with, just with this expression, what we will end up with is dn1, dn2, alpha plus minus 1 minus alpha to the power dn1 plus dn2 to the power alpha. So this is what minus. This is what we end up with, and on this now apply. On this now apply. So observe that. So let me this now. So dn1 plus dn2 to the power 2 plus alpha is bigger than equal to 4 times dn1 dn2. So this is the 2 part, and dn1 plus dn2 to the power alpha. Right? So this is, remember, this is the xn part. It's exactly the function of x. So so this to the power. So I have this to the power alpha. So dn1 plus dn2 whole thing to the power alpha is bigger than equal to 4 to the power alpha by 2 plus alpha, and xn to the power alpha by 2 plus alpha. So minus of that becomes I is less than equal to, and that is the inequality that you get. That is that you see the C alpha that you get. It's 4 to the power this, 4 to the power alpha by alpha is 1 minus alpha. That is the C alpha thing that you get. Okay. So this is essentially a proof of you have to write down this expression, multiply, and do the algebra. That's not straightforward algebra, and take the expectation, and that gives you this expression. The other part, I am not going into this. So we have taken a result from Menshikov and extended it for, so Menshikov's case when we had was a particular case when these were integers. So we have now extended it to non-integer case, and so their case was like 2k and k. So that kind of case, we have now extended it to any general alpha beta. Okay, and that's the and then again this kind of similar. What you have to do is make a super martingale with like x, so essentially xn plus some constant times n minimum tau n. A minimum tau, and this minimum tau b, this to the power suitable power. So this to the power, we are taking beta by beta minus alpha. So this would be a super particle. That's what you need to show. Okay, and you take this expression that would give. And just I will say one word about the where is the theorem? Yes. So here we had taken these random walks with increment plus minus 1. But if you take more general random walks, but with finite increments, so what we can show is that this expectation is finite, and for some constant C1. So what we can show is that C1 times this plus C2 times 2i plus 2j plus some constant. For this is for random walks with finite increments. So then now they can cross over without hitting, but still they will hit, and we can show in that case we have not been able to show 1 plus alpha by 2, but to the power just expectation of the random first collision time still bounded, and the leading term is 2i times 2. Okay, so I'll stop.
Two questions.
This is for tau squaring or tau collision. Now, trace from before.
Which one?
That's the expected time, right?
This is the expected time.
Not the half.
This is the expected time.
I know,
Three
in your for this 2i, 2j, that's there's
No.
a half somewhere. That's
No. Half is 1 plus alpha by 2, that half remain. So this is for the case when the increments are not plus minus 1. They are more general, so they can cross over without hitting. Here they cannot cross over. That's why I had kept the third part, because they can happen that they can cross and hit.
How much you know about the tail behavior?
For this, it behaves essentially expected that it behaves like 3 to the power my n to the power 3 by 2. Maybe there is a logarithmic correction is there, but that is not
That is what is not known.
no, not known. And that for that is this, I think nothing is not too much.
If there is no more question, let's end. Our next speaker is Professor Antor Bandyopadhyay, Head Degree Center. He will speak on interactive and.
All right. Thank you so much, Kumar ji. And I'd like to start by thanking Professor Rahul for being very strong encouragement for all of us who like probability theory since the time we started learning it. Now, there are a lot of things one can, and I'm sure in today and tomorrow we'll hear people will talk about Professor Rahul, as there are many great things we can admire about him. One thing which I find always very interesting, that you can discuss with him on many matters, be it politics, be it books, literature, ISI matters, but those discussions in general last for a few minutes. Almost immediately, Professor Roy would like to discuss something mathematics, something to do with probability, something he has read, something he's thinking. So that's really an admirable thing, and I think in the corridors of ISI Delhi, in the faculty block, a lot of academic discussions gets initiated because of Professor Roy. And I strongly hope, seriously hope that that will continue, irrespective of the administrative matter that he will be retiring by the end of the month. Now, what I'm going to talk today, it has some root to some discussions with Professor Roy long time back when I joined. And one such thing was discussed. So Professor Roy, myself, and Anisha